Yeah, shall we start?
Yes, sir.
Okay, so the next we are going to see the kinetics of various order reaction. That is zero order, first order, second order. We have to see. We have to look at the expression of the relation of the concentration and temperature, concentration with time. Sorry, for different order reactions. Okay, all these things we are discussing under concentration only. Like I said, concentration, and the rate of the reaction has a complicated order because there's a term over there which is called the order of the reaction, which can be anything 0, 1, 2, 3. Based on that, we have the relation of rate and concentration. Okay, so now we are going to see with time how concentration varies depending upon the various order reactions. Correct. So first we are going to see here zero order reaction. Zero order reaction. Okay, suppose we have a reaction that is A gives product and we are assuming this as a zero order reaction. How to find out the relation of concentration and time? Correct. So we can say the rate for this reaction is equals to minus D concentration of A by dt. Okay, D concentration of A by dt. And if you relate this with the law of mass action relation, that is rate equals to the rate constant K into the concentration of the reactant species to the power the order of the reaction, right? So did you understand this relation? Minus dA by dt is the rate, right? Change in concentration by time. And this we can also relate with law of mass action, that is K into concentration of A at any time T to the power the order of the reaction, which is 0. Clear? Understood? Yes. So this A to the power 0 is 1 only. So we can solve this expression like minus dA by dt, or we can write this as K times dt here, which we can integrate and we can solve, right? Yes, so we have differential equation here, and this differential equation you need to solve, right, in order to get the relation of concentration and time. Okay, so this we can integrate, we can place the limit and we can integrate here. So here we are integrating this and this. At time t is equals to 0, the initial concentration, suppose I am assuming as A naught, t is equals to 0, the concentration is A naught. At time t is equals to t, the concentration is suppose A t we have. Okay, so when you solve this, you'll get the equation concentration at any time t is equals to the initial concentration A naught minus K t. No doubt. So this is the relation of concentration and time for zero order reaction. Done? Okay. Now the important thing here is, you see the rate of the reaction is constant, right? It is not varying with temperature, sorry, with concentration, because concentration to the power 0 we have. So it is independent of the concentration term. Okay. Write down zero order reaction proceeds with a constant rate, hence goes to the completion. Right? Rate is constant over here. If you see the graph here, 2-3 graphs we have. So this is concentration and this is time graph here. Concentration and time graph, you see it will be a straight line. Y is equals to mx plus c, the form we have, where this point here, this point would be a naught by k, coordinate is this, and here the coordinate is, we'll put t is equals to 0 and we'll get 0 a naught. Right? Slope of this line you also know that is k. This graph you see, this is the graph of rate, that is dx by dt, and this is time, or we can take concentration. So like I said, rate is constant because it is independent of concentration. So as the time proceeds, the rate is not changing, and this will be a constant straight line we have like this. Okay. Concentration of product varies linearly with time. Okay. So concentration of product and time graph, if you see, the first one was for reactant, and this graph will be like this. Initially it is 0 and then it varies linearly. Y is equals to mx. There's a term called half-life. Okay. So we call it as half-life time or half-life period, represented by T half or T50. Okay. It is a time taken, it is the time taken by the reaction for 50% completion, T half. Okay. So when we have T is equals to T half, the reaction or the concentration left at time T half is equals to initial concentration divided by 2. So if I substitute this into the equation, we get A naught by 2 is equals to A naught minus KT half. So from this, if you solve T half, you'll get what? T half is equals to A naught by 2K. Very important relation. They ask this question of half-life many times, okay, for various order reactions. In fact, we calculate T half in all the various order, okay. So for first order, what we can conclude, for first order, the reaction lifetime, half-lifetime, is directly proportional to the initial concentration, which is logically correct also. More concentration if you have initially, it will take more time to finish half of the reaction, right? So this is the relation we have here. Okay. Now some examples we have of zero order reaction that you should memorize. Examples of zero order reaction. Like photochemical reaction that we have. Photochemical reactions are zero order reaction. H2 plus Cl2 gives, in presence of light, gives 2HCl. So this reaction depends on the intensity of light. Depends on the intensity of light. More intensity, faster will be the rate. Okay. Another example we have discussed, dissociation of gas at solid surface at high pressure. That is also zero order. Example, 2NH3 dissociates into N2 plus 3H2. Zero order. High pressure. 4PH3, P4 plus 6H2. All these are zero order reaction. Finished, copied? Okay, now one very important, relation here. With this, you can find out the answer, directly. See, we have initial concentration one side, and here we have time. So when initial concentration is, suppose I am taking A naught, then the time is 0. This becomes A naught minus KT according to the equation that we have got just now for zero order at time t, right? If you have 2t here, double time of this, then this would be A naught minus 2 KT. If it is 3t, A naught minus 3 KT, and so on we can go. Correct? What is this pattern? Can you tell me? What is this pattern we have? We have equal interval, right? That is of KT. Yes, what is this pattern?
AP.
The pattern is AP, isn't it? Equal time interval, equal amount react. Can we say that?
Yes, sir.
Yes, yes, respond.
Yes, sir.
Right. So we can say the concentration of reactant for a zero order reaction, right, in equal time interval follows the pattern of AP. Okay, right on this point, the concentration of reactant react in equal time interval. The concentration of reactant react in equal time interval concentration of reactant react in equal time interval follows the pattern of AP, arithmetic progression. Right? Follows the pattern of AP, arithmetic progression, with a common difference. What is the common difference we have in this? Common difference is K times into T. So if you know this, if you keep this in mind, any time interval you can find out. Okay, this directly you can find out without using the equation. Okay, so we can say KT amount is getting react in this equal time interval. The amount is reacting is this only, KT, right? It means in equal time interval, equal amount react in zero order reaction, right? Next point to write down. This means in equal time interval, the amount of reactant reacts is equal. In equal time interval, the amount of reactant reacts is equal. What is the advantage of this information? Suppose a reaction we have, initially concentration is 100 and 100 to 80, suppose you are going, right? Like the question is given, for a zero order reaction, initial concentration is 100 and it goes to till 80 concentration, means A naught is this and 80 is this given, right? And for this, the time is given that in this time, this reaction takes place, this conversion happens, 100 to 80. Then the second part of the question is what? If you start with the concentration 60, right? If you start with the concentration 60, then for the same time, what is the amount of reactant left here? Are you getting this question?
40.
Right? The question is, you start with 100, in some time you'll get 80, the concentration of the reactant. For the same order, for the same reaction, if you start with this concentration, in the same time, what is the amount of reactant left? So obviously you can use that 80 is equals to this reaction, you can use A naught minus KT. From the first set of data, you can find out K, and with this K, you have A naught, T, you can find out 80 again here. That is also you can do, the method is that only. But it will take time. Okay, what I'm telling you, with this information, at equal time, equal amount react. Okay, so 100 to 80, it becomes 20 reacts in this time. So here also, whatever initial concentration you take, In the same time, same amount will get react. Hence, 40 is left over here. You don't have to write anything in this question. Yes, understood?
Yes, sir.
Correct. So nothing you have to write in this one. Other way also, suppose they ask you time also here, that for this conversion, this time, we take for this conversion 60 to 40, what is the time required? Okay, again the same time here because the same amount is getting reacted. Okay, so very simple one, this property you must keep in mind. Okay, so this is the one thing we have, that equal amount reacts in equal time for zero order reaction. T half expression is important. T half is directly proportional to initial concentration. You see, I have already told you that zero order reaction rate is independent of concentration, right? So no matter whether you take 100 or you take 60 or you take 10, for the same amount, same will be the time will be taken. 1 second. Yeah, so this is for zero order reaction. Similarly, we can derive the relation for first order reaction also. Second type of reaction you write down, first order reaction. Again, same thing we have to do. Suppose a reaction we have, A gives product and it is the first order reaction we are assuming, correct? So the expression would be what? At time t is equals to 0, a little bit it's not required. We can simply write rate is equals to minus d concentration of A by dt, which is equals to the rate constant K into concentration of A at any time t to the power 1. Okay, now when you solve this differential equation, you'll get the relation of concentration and time again. So that would be minus, we can write down dA by dt, sorry, dA by concentration of A is equals to minus K dt. When time t is equals to 0, the concentration I'm assuming A naught. When time t is equals to t, the concentration is AT. And when you solve this, you'll get K is equals to 1 by T ln A naught by AT. A naught by AT. Which we can also write, you see, in this expression, we can write it as A naught by AT is equals to e to the power kt. Hence, AT is equals to concentration at any time t is equals to A naught e to the power minus kt. This is also we can write. A naught e to the power minus kt. AT is the amount of reactant A left at time t. Could you tell me the expression for T half here? What is the expression for T half? We can substitute here simply, right? So at T is equals to T half, the concentration AT becomes A naught by 2. And this we can substitute in the expression, that is K is equals to 1 by T half ln of A naught by A naught by 2, that is ln 2 here. So T half is equals to 0.693, the value of ln 2 by K. Yeah, ln 2 by K. So you see T half is constant here. It's constant, right? Because K is a constant. It is independent of time, right? K does not depend upon time. K is independent, so T half is constant for first order, and it is independent of concentration also. Independent of initial concentration. What do you understand by constant T half? Means what? Whatever initial concentration you take, T half won't change. It will be same. Okay. The example of first order reactions are, write down, it is the acidic hydrolysis of esters. Acidic hydrolysis of esters. Inversion of cane sugar. Inversion of cane sugar. Decomposition reaction, like we have 2N2O5 gas decomposes into 2N2O4 gas plus O2. Decomposition reaction. Problems related to the reactions related to radioactivity. Radioactivity, growth and decay of bacteria. Growth and decay of bacteria. That is also first order reaction. Okay. One more thing we have, in which when you heat the disonium salt, C6H5N2Cl, and when you heat it, it forms C6H5Cl and nitrogen gas evolves. All these are first order reaction. Okay, first order reaction. Then, now you see one more pattern here. At time t is equals to 0, what is the concentration we have? A naught initial concentration. At time t is equals to t, what will be the concentration? A naught e to the power minus kt. Look at the formula I have given you before in the previous page. A naught e to the power minus kt at time t is equals to 2t. It is A naught e to the power minus 2 kt. Then it is 3t A naught e to the power minus 3 kt, correct? So what is this pattern?
GP.
This forms a GP, right? The common ratio. What is the common ratio we have here?
E minus KT.
This forms a geometric progression with the common ratio e to the power kt. Okay, A naught by A naught e to the power minus kt, common ratio is e to the power kt. So in this, what happens, since we have the common ratio, so when the reaction is of first order, then
So
you can, sorry?
shouldn't it be e to the power minus KT?
Oh, we'll write second term by first term, no? 2, 4, 8 second, plus minus you write down, missed it. Yeah. Second term by first term, this
Sir,
way.
could you go to that previous slide? I wanted to.
This one,
Yes, sir.
copy this.
Yes, sir, done.
Okay. So in this, what happens if we calculate equal percentage since we have ratio here, so equal percentage reacts in equal time. Percentage reacts in equal time. Okay. So for example, if suppose 100 to 90 you are going in 10 seconds, then 10 seconds, sorry, 10 seconds. Okay. So if you start with initial concentration 90, then what is the amount of concentration we have left here after 10 seconds? You have this information. 81, right? Equal percentage react, 10% react here. So here also in 10 seconds, 10% only react. So 90 ka 10% is 9. So 90 out of 9, 90 minus 9 is 81 that is left here. So always remember in first order it is GP. We are talking about equal percentage here in equal time. And in AP, that is the zero order reaction, it is equal amount reacts in equal time. So the first one we have amounts, here we have percentage. Fine. Now the last thing in this is the graph. Okay, so this one is concentration of reactant and this is time. So it has the initial concentration maximum And with time, the concentration decreases. The graph is logarithmic, so it will be a curve like this. Okay, it goes to a minima, it will be a curve like this. Right? Rate and time graph, if you see, it is also very important. Rate and time graph, since the concentration decreases with time, so at time t is equals to 0, the rate will be maximum. Okay, and with time, the rate also decreases. It won't become 0 because reaction won't be complete, because at 98% of the completion of reaction, we assume that the reaction is over because the rate becomes extremely slow, right? And hence, it won't touch the x-axis, that we don't assume. What is the graph of log of concentration and time? This will be a straight line with negative slope because we have log of AT is equals to log of A naught minus 2.303 kT. You can take ln also correspondingly, you can find out. Okay, so this intercept, y-intercept we have here is log of A naught, right? The slope here is again 2.303 K we have, and this two coordinate also you can find out. Done? Okay. Next, we'll do second order reaction, and then we'll do some problems on this. Okay, all three order we'll see, and then we'll do some problems. So heading you write down second order. Could you find out the relation of concentration and time in this second order reaction? I'll write down the expression A gives product, and then it is rate equals to minus D concentration of A by dt is equals to K into A square, since the order is 2. Done. One second. Yeah. So when you solve this differential equation, the relation of K concentration time we have, we can write K is equals to 1 by T, 1 by AT minus concentration of A at any time T minus 1 by A naught. This is the relation we get. T half, if you calculate, I'm just writing it down. It's a simple thing. In AT, you can substitute A naught by 2. T half is equals to 1 by K times A naught. Okay, so for the second order reaction, you see, T half is inversely proportional to the initial concentration we have. So for zero order, it was directly proportional, then independent, and here it becomes inversely proportional. Okay. In this, we don't have any such pattern like APGP we already had. So we don't have any pattern here. Graph we'll see quickly here. Rate and concentration graph we have. So this graph is the rate and concentration. This graph is for rate and concentration square. This graph is, we have 1 by concentration of reactant and time, right? So this graph, it goes like this. Rate initially is 0 and it increases this way. Right? Rate and concentration is square we have. It is a straight line passing through origin, like this it goes. This graph will have here a straight line from this point with a positive slope. Right? This is 1 by A naught we have. One more graph we have. That is T half and 1 by A naught, initial concentration. This will also be a straight line passing through origin. Done? All of you copied? Finished? Yeah. Next, we'll see some questions on this. So, this question you try. Yes, what is the answer? 2. Twice of it you are getting. Okay. First order reaction, calculate the ratio between the time taken to complete 3/4 of the reaction and time taken to complete half the reaction. First order reaction, right? So first order, we know T half is equals to what?
ln2 by k.
Okay. And time taken to complete this reaction T3 by 4 is equals to 1 by k ln A naught divided by A naught minus 3 A naught by 4, because this one will react. So it is 1 by 4, so ln 4 by k. So T3 by 4, we are getting it as ln 4 by k. You can take the ratio, you'll get twice of it, right? 2 into 3 by 4 is equals to 2 into half is equals to T3 by 4, correct? Twice of T half. This is one thing, right? Twice of 3 half, you get this. 3 by 4, I'm sorry. Now, directly if you do, see, we have 100, suppose the concentration. You can do it directly without using any formula. If 3 by 4 of this react, what is left? So 100 minus 100 of 3 by 4, that is 25 left here. Means if you go for one half life, right, it will be 50 here. For another half life, it will be 25. Means from here to here, if you want to go, you have to use 2 half life of it, right? That's why you see the time required for this change is twice of the half life. Directly you can say 2. Did you understand this? What I said? right? So without using any formula, you can use directly. Assume some value, okay, and then you can find it. Suppose if they give you 3/5 of the volume react, okay, or 3/6, suppose, or something like the 3/7, suppose if it is react, then try to take the multiple of 7 here, the initial concentration, so that the calculation will be easier. Okay, that kind of change you can do always. Okay, this question you see. This one you try. Did you do this?
Yes.
Done. Simple. This you need to prove, right? So just you need to use the expression, and you can do this. Or what you can do, you can write down, take the ratio. If the ratio is coming out to be 1, then it is equal. Simple. So easier way is what this kind of question you'll get in board exam. Okay, not in JEE and all. Board exam you'll have this kind of question. So T of 99.9% divided by T of 50%, right? That will be what? Best thing is K and K will get cancelled. You will have, ln of percent if it is there. So I'll assume 100. 100 divided by 100 minus 99.9 divided by ln 2, right?
So could we also do it by taking
This one is ln 2 is 0.30, and this you will get ln of 10 to the power 3, 0.3, Acha, 0.3 I have written, so on the top it would be log, no, correct. So if I take here as log, so this would be 0.30, and here it will be log of 10 to the power 3. Anything is missing in this expression?
So this got it only,
By
sir.
100 minus 99.
Yes, sir.
And this would be
So
ln2.
this will come as 10 only.
Yes,
is
sir.
correct
It will
only.
come.
Yes, sir.
Yes, sir. It's correct.
That's right. So I'm getting 3
So why
log
0.3
10
will
times
be
if it is there. Oh, I was thinking
Sir, it will
it is
come as
equal.
10.
That's what. Fine only. So 3 log 10 divided by 0.3, right? So we are getting 10 here. So T 99.9% is 10 times of T50. Very simple, you can do this. Right, so both in this kind of question they ask. This question you see, 2 questions are there in this. Yeah, this one you try. T.75 means 3/4 of the reaction has been complete, has been done, right? 3/4. Fiftieth. Okay. So first one you see, the best way is to, without using any formula, you can do this. It is given T3/4 is 1386. Okay, so we have the reaction, it is T half and plus one more T half. This from here to here, it is T1 3 by 4, correct? So T 3 by 4 is always equals to, we can write 2 times of T half. Okay, so 2 times of T half is equals to 1386 given in the question. So T half is 0.693 by K. So it is 0.693 by K is equals to 6, 9 and 3. So K is equals to what? K, we got it as 10 to the power minus 3. 10 to the power minus 3 second, because the order is 1, so only time will be there, time inverse. So this is the order here. Now, the second question you see, in the first order reaction, the concentration of the reactant decreases from 0.8 to 0.4, that is 15 a minute. So T half is given in the question is 15 minute. Okay, the time taken for the concentration to change from 0.1 to 0.025. So you see 0.1 to 0.05, it is half of it. It will take 15 minutes, and 0.05 to 0.025, one more half-life we require, right? So the total time will be 2 times of T half. Directly you can say 30 minutes is the answer. Any doubt in this? Yes. So no need to, use formula. Directly you can do like this. What is the initial rate you are getting? Yeah, initial rate is fine. 8 into 10 to the power minus 9. That's correct. Determine the rate after 0.04 mole per liter of A has been reacted. 3.88 10 to the power minus 9. That's correct. Yeah, 3.88 10 to the minus 9 is correct. So what you have to keep in mind here, first of all, rate is given. What is the order of the reaction here?
Pseudo.
Third order, right? Okay. So for this initial rate of the reaction with A is this, and this it is given. So 0.1 and 0.2 it is given. So directly we can find out the rate, that is K is 2.0 into 10 to the power minus 6. A is 0.1 and B is 0.2 square. So you solve this, you'll get the initial rate. Okay, so I'm not going to solve this. B is what? Determine the rate after 0.04 mole of A reacted. So always you see when you write down the rate expression, K into concentration of A, B square here. This A and B, the concentration that we have, it is a concentration left. Okay, A and B is the concentration left. So you need to find out that when 0.04 mole per liter of A has reacted, then what is the mole of A has been left, right? And what is the mole of B has been left? Okay. So the reaction is given here. First of all, I'll calculate here the mole of A left. Initially it was 0.1 minus 0.04. So it is 0.06 mole per liter of A left. Okay. For B, what is the amount left? For that, we should write down the rate expression for A and B. That is 1/2 minus D concentration of A by dt is equals to minus dB by dt. Right? Okay, so the B that reacts here, that is minus dB by dt is equals to half of concentration change in B is 0.04 because that is the amount of A has been reacted. So it is 0.02. B left is what? B left is initially the B is 0.2 minus the amount which reacts, you need to subtract, and this is 0.18, right, of B left. So now this value and this value you need to substitute here and here, you'll get the answer as the new rate. So answer for the new rate is 3.88 into 10 to the power minus 9. Okay, so all of you have done this as I've explained this. So must keep this in mind. This A and B is the amount of AB that is left. Okay, one question we'll see, this one has been asked in JEE exam. Yeah. Okay, half-life is 127 hours. Close. Yeah, 5.4 is, yeah, you can say it's close. Yes. The answer given is 5.2. Yeah, right, Ruchira. I saw your answer in seconds. Yeah. Okay. Percentage they're asking. So you just find out, you just assume it as 100, the initial one, and then you can find out, okay, what is the half-life? So half-life, simple, you can calculate T half is equals to 0.693 by K, right? You'll get the answer. And what percentage of initial concentration would have been changed? Means the amount that has been reacted, we need to find out, correct? So K is equals to 1 by T ln of 100 divided by 100 minus X, right? 2.303 you can multiply, but keep one thing in mind, K is given in second, this time you have to convert in second. So this would be 1.5 into 10 to the power minus 6 equals to 2.303, time is 10 hour, so 10 into 3600 seconds log of 100 by 100 minus X. That is what X you need to solve, since the initially we have assumed it is 100. So the answer will be X. Whatever X you get, that will be the answer. Okay, fine. One last thing we'll discuss for today, that is we have discussed first order, zero order, second order reaction, and the expression of concentration with time for various different order reaction, correct? If sometimes what happens, they'll give you nth order reaction, and you should know the relation of nth order with time. So we are assuming, or we are doing next, the kinetics of nth order reaction. So same thing, if A gives product here, nth order reaction, so we can write rate is equals to minus D concentration of A by dt is equals to K times concentration of A to the power n. Then we'll have D concentration of A by A to the power n integration minus K dt. Okay, integration, it is 0 to t, A naught to AT. Could you find out the expression of this time and concentration? Done? Okay. Yeah, so in this one, the expression that you get, okay, I'll write down the expression here directly. Okay, you can derive it. The expression is AT, concentration at time t, to the power 1 minus n, minus concentration, that is initially we have, to the power again 1 minus n is equals to n minus 1 k into t. This is what you will get. Where this n does not equal to 1. It is not valid for first order, because again the expression will not be valid there. Okay. Could you find out T half from this? I want you to find out the relation of T half and A naught in this, because on this only they'll ask question. T half and A naught. Okay, the expression of T half you get here. T half is equals to 1 by n minus 1 into k, the rate constant, A naught to the power 1 minus n, open bracket, 1 by 2 to the power 1 minus n minus 1. This is the expression you get. And the t half is directly proportional to A naught to the power 1 minus n. This is the expression we have here. But this is true here. You can see it is valid for any value of n. Not important, but we have this relation. Okay, this is the nth order kinetics. Okay, one last thing we'll discuss for today. That is pseudo first order reaction. It's theoretical thing. Here you won't get any numerical. Just you need to have this information, that is it. Pseudo first order reaction. Write down the statement first. Due to excess amount of one of the reactant, due to excess of one of the reactant, a second order reaction write down like this, a second order reaction starts behaving as first order reaction. This kind of reaction, we call it as pseudo first order reaction. This kind of reaction is pseudo first order reaction. The examples we have already done, you see, hydrolysis of esters. Hydrolysis of ester. The reaction is, for example, CS3COO, C2H5 plus H2O excess in presence of acid, it converts into CS3COOH and C2H5OH. So water is present in excess here. The rate expression is independent of water. It is directly proportional to CS3COO, C2H5, right? So order of the reaction is 1 here. N is equals to 1. Excess reactant, we don't consider. Okay, second example we have inversion of cane sugar. Here also we have same thing, C12 H22O11 plus H2O excess. This converts into C6H12O6 and C6H12O6. Okay. Here also the rate is equals to K times of C12H22O11. Third example, write down esterification of anhydride. esterification of anhydride is also one example of it. Metabolism of hormones in human bodies, again pseudo first order reaction. Sometimes they ask this question like which of this reaction or what is the example of pseudo first order reaction. Okay, just you need to know this. So metabolism of hormones in human bodies. Okay, so this is it for today. Okay, we have done a lot of things. Next class will start with first order growth kinetics. Okay, it's a small thing, and what expression we have in case of gaseous phase reaction, we'll see that. Okay, and then few topics we are left with, that is reversible reaction and parallel reaction, and then we'll go to the second part, that is mechanism of the reaction. What idea we'll have from the mechanism of reaction. These things will continue in the next class. Okay. Last example is metabolism of hormones in human bodies. Okay. Fine. Thank you. I'll share one assignment on this. You can solve that. Okay. Yeah. Thank you so much, guys. Take care. Bye.
Thank you, sir.
Thank you, sir. Thank you, sir.